try this out. Oh, I'm just trying to see if I can flip my camera first. What's going on, everybody? I actually just want to see, before I do anything, if I can actually flip my camera. Test. 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 Can everyone hear me? Hold up that.
There he is.
Hey, what's going on?
Hey, this is kind of funny because I can see you on the Zoom and I can see you down here. There's a slight delay.
Oh yeah. So what's gonna happen is pretty soon I'm gonna move my phone so that everyone can see the screen in a second.
Okay.
I'm trying to flip my camera. That way everyone can see the other stuff. Do you know how to do that? I'm like having such a hard time with that.
Let's see. Is it under
I feel like,
more?
I feel like such a boomer right now. Oh my goodness. My goodness.
I actually don't know. I've seen it done.
Right?
Maybe not. I think I've seen it done. Maybe people were just using filters.
Otherwise, I mean, that's fine. I'll just kind of flip my camera
Flip
around
the
if that's
camera.
the case. Yeah, that is so odd. It's funny. I looked it up and it told me that all I have to do is double tap, but that's not happening. So I'll have to see in
Oh,
a second.
that sends myself likes. That's kind of funny.
Right? Yeah. So if anyone in the comments knows how to flip the camera while on live, please let me know. Otherwise, I'm just gonna I'll kind of improvise. You know?
We'll make it work.
Yeah, exactly. So anyway, I saw that you were busy with Serbo Bear just a few minutes ago.
Yeah, he invited me to do a live too this morning, and I was like, "Yeah, we can do two in one day. We can do
Yeah.
this."
Yeah, that's kind of fun. Yeah. I was in there for a little bit and I saw you talking about like you were you were visiting different countries in like in Spain and stuff, right?
Yes, I love world travel. So that's really my hobby. I love to get around and not just go to tourist destinations, but actually get
Hmm.
to know the people and the culture. And so I have actually lived in Spain. I've lived in Nicaragua, Honduras, Guatemala, Ecuador. Uh, I think that's it for the living. And then I visited a lot of other countries too, but that's more touristy. But you get to live with the people, shop in their stores, go to their churches, go to their schools, get to
Yeah.
know what their culture is really like authentically. And it's just really an amazing experience.
Right. Yeah. There's something about traveling. I mean, it's just one of those things like you can see it on YouTube. You can see how people live, through video, but being in there is just a whole different experience, you know?
Yep.
Yeah.
I agree
That's
100%.
awesome. Yeah. So for everyone that is on the live on mine and on yours, I mean, do you want to kind of introduce yourself, a little background as to what you do and what got you into math?
Sure. Well, I'm Tyler Wallace. I'm a math instructor in Washington State, and I think you're in Washington as well, if I remember right.
I am,
And I
yeah.
teach at one of the community colleges here in the state. I love teaching at a community college because I love the mission of the community college that believes that every student should have a shot at a higher education. So it's
Mm,
more affordable than the big universities. It's not exclusive like the big elite universities. It's a place where anybody can come and get an education. We're going to meet you where you're at and we're going to help you be successful. And it's really
mm,
about the learning here, not about the instructors doing their own original research. All the instructors here want to help our students be successful and open up those opportunities beyond their imagination. So I love being part of that mission. I originally was going to be a computer scientist. That was my goal. In the late 90s, early 2000s, everybody was programming, and that was the new exciting thing. And as a person studying computer science, you have to take a lot of math. And so I took the math with that. And by accident, got a summer job working in a student tutoring center and just
mm.
fell in love with math education. And I thought, this is my in to help others be successful and open up those opportunities. This is what I want to do. Changed my major, studied math, got a pure math degree from George Fox University, later from the University of Houston. And I've been teaching math since 2005 at various
Wow.
levels. I've done middle school, high school, and college. I'm at the college now, and it's definitely my favorite because at the community college, we get those dual enrollment high school students, but we also get those
Hmm.
people coming back for a new career. You get the whole gamut, which I really enjoy. So that's
Wow, that's
me in a
incredible.
nutshell. And I make TikToks for fun, and for some reason, people are following me. So we're having fun with that. Math talk community is what it's kind of come to known as.
I love it. I love it. And I kind of actually wanted to talk about that since you were just mentioning TikTok. So you're obviously big on TikTok. You have like almost 80,000. You want to get to 100K and even more. Um, and I'm watching your videos and I just can't. It's fascinating how you find the sounds and you kind of play around with it. You make a whole scenario about it. So can you kind of walk us through the process of how you find the sounds in general that you want to use and what kind of goes in your head when you're trying to create that one TikTok?
Yeah, so that's it's different, probably different for everyone. Sometimes I'll be scrolling my FYP and there's a sound where I'm just like, oh, that is talking about the chain rule. I just something about it just screams chain rule. And so I make up a chain rule problem and apply it. Other ones I'm like, that is a hilarious sound. I need to find a way to use it. My
Yeah.
great example of that is there's the one where there's the sniper and he's like, the one on the left, and they fire. And he's like, that's my son. You must protect him at all costs. And they're like, oh,
Yeah.
crap. And I was like, everyone, I saw that like 4 or 5 times in the same day on my FYP. And I was like, it is hilarious every time. I've got to make it about math. And so what do we do in math that we do competently and we're proud of, and then realize, crap, I have done a terrible thing. And to me, it just popped in my head, hey, we're canceling terms. You can't cancel terms. You reduce factors, but not terms. Factors are multiplied, terms are added. Addition, we hate addition in math. That's why we spend so much time talking about factoring, because addition, terms, we can't do much with. We can't take radicals of terms. We can't take exponents of terms. We can't multiply exponents into terms. We can't reduce terms. They're just very inconvenient. But we can do all of that stuff with factors. And so that popped into my head as something that we do confidently, cancel those terms, but it's wrong. And so I made a whole video where I confidently took out the one on the left. I canceled the terms on the left. And then they were like, here's my son. Ah, bring back the terms. And it was too late. It was hilarious. It was a lot of fun. So that's kind of how I do it. I just play and have fun with it and think, what might this connect to? And also really just trying to make math, take away the scariness of math. That's really one of my big goals. A lot of people think math is scary and hard and I'll never be successful. And I want to show them that math is fun. We can have fun with math. We can laugh at math. We can enjoy it and make it relevant to whatever crazy trend you're going to see. And so that's it. And I have fun with it. It's my creative outlet, I guess. I like to take a half-hour break every day from work and just make a few TikToks and laugh at myself. And some of them never get posted because they never work out. Others of them I'm really proud of, and I put them out there and they get 200 views. And others I spend 5 seconds on and they get 2.4 million views. I don't know what the system is.
The algorithm just picks up whatever it likes and it just runs with it, you know?
Yep.
Yeah, I think the last time we met on a live, you had mentioned how math just needs to be marketed differently, and I think the way you create your stuff, there's other math creators. I like to call them creators that do the same thing, and it could be the same concept, but we all explain it differently, and I think that goes with how you should learn math. Whether I'm taking something like derivatives, for example, like we're going to do right now, you can have one way of doing it. I can have a different way of doing it. Another person could have, a different method that they're going to use. And I think that's part of what TikTok is doing as us math TikTokers, if you will. We're marketing those concepts pretty well. So thank you for that. I think you make it really fun. And I'm kind of jealous sometimes that you can actually create some of these things. And I didn't come up with it.
Well, you have a lot of good stuff too, so don't sell yourself short.
I try. Okay, so I'm gonna try this thing. I'm gonna move my camera so that everyone can see what I have. And does anyone have an idea of how we flip that camera around? Because it's still not working for me, which is so upsetting.
I've got a comment that says it should be in settings, but I am not seeing it in settings.
Right? Pause. Maybe admin settings.
No, block people. And I can rank people. Oh, that's interesting.
Yeah, that's kind of cool. Okay, well, you know what? Guys, whoever's watching my stuff, how about I'm going to end my live and you just re-invite me and I'll switch the camera around.
Oh, okay.
Could that work? Would you still be live on your end?
Yeah, I'll still be live if you disconnect.
Okay, cool. So I'm going to disconnect and then just invite me back in like within a few seconds.
Okay.
All right, I'll see you in a bit.
All right. I got some. And, oh, there we go.
We're back. Okay, so now it's a little different. You're only going to see me on the camera there. So just like you mentioned, it might be a little delayed, right?
Yeah, but that's okay.
Yeah, absolutely. Hold on, I'm gonna move this. All right. Well, we're talking about derivatives here. So as as we're trying to solve these, what are some sort of advice that you would give students whenever they are trying to go about taking the derivative of any function?
Well, before I dive in with any derivative, I try and figure out what's happening structurally with the problem. What pieces is it made up of? Because those pieces are going to be what inform me and how I can go forward to solving. So like for this
Hmm.
one that you've got up here on the whiteboard, the pieces I see are two separate terms. And what's nice about derivatives is we can handle the terms one at a time. And so we've got our derivative rule, the power rule, which says that I can just move that exponent down. Let's see if I can do that. I'm going
Hmm.
to move that exponent down in front and multiply those numbers. So 5 times 4 gives me 20. And then we know we can reduce the exponent by 1. Keeping the minus sign, then I'm going to do the exact same thing here. 5 times 4 is also 20. But this time I'm going to reduce the exponent down by 1 to get cubed. And so I think you're starting really nice with me and starting with a simple polynomial. That was generous. I was saying
Right.
in my previous live, I'm a little nervous what you prepared for me and how mean you're going to be. So that was a nice one to start with.
Yeah. Well, you know what? At the same time, I want to make sure that students also, can solve these maybe on their own if they have a piece of paper and they want to write things down.
Excellent.
Yeah.
Yeah, I'll try and talk about each one a little bit first to give them a chance to try it on their own.
Perfect. Okay, so let me go ahead and let's go to the next one then. Let's go ahead and scroll
No, if
down.
I
I
can
have
make keystroke a little thicker.
no. Yeah, let's try that. Okay,
Oh,
here we
wow. We
go.
just escalated significantly from the first problem. All right. So, there's two ways that we could tackle this one. So as I'm looking at the pieces here, I see the big division makes me think quotient rule, first thing. But actually, I now see three ways to do it.
Mm-hmm.
Another way, so yes, there's a quotient rule in here. The problem is in the numerator and the denominator, there's a lot of stuff going on. I wonder if in the numerator, I could either use the chain rule to work that out,
Right.
or we can multiply it out and then just use the quotient rule.
I like it.
So let's try treating it like a big quotient rule though, and we'll use some chain rule along the way.
Okay, perfect.
So I like to remember the little jingle that is low d high minus high d low, and then I'm going to square the bottom, and away I'll go. And if it
I like
rhymes,
it.
that means I got them in the right order. So it's d low on the second part with the square the bottom, and away I go.
Mm-hmm.
So what that says to me is when I say high, I'm talking about the top part. And when I say low or bottom, I'm talking about the bottom part. So first I take the low, which is the bottom. So I'm going to have an x squared plus 7 to the x. And then I'm going to multiply by the derivative of the high, the derivative of the top. So as I do the derivative of the top, we're going to treat this like a chain rule because we've got stuff here that is squared. I don't know if you can see that in the
Yeah,
little
we can
screen.
see it.
I'm writing kind of small. Let me know if I start writing too small because I look up at the
No, do your
screen.
thing.
So using that same exponent rule we saw in the previous problem, I'm going to bring the 2 out front. 2 times 4 is 8 times the stuff, which is 3x minus 1 squared. I'm going to run out of space. That's okay. And then I have to multiply by the inside, the derivative of the inside. And so when I look at the derivative of 3x, that derivative is just 3.
Perfect.
So that's my low d high. Now I'm going to do minus high. So that's the top part again. But this top part just like it exists originally, which is 4 times 3x minus 1 squared times the d low, which I need to be careful. parentheses are a common error I see a lot. They'll just do the derivative of x squared plus the derivative of 7 to the x. So I'm going to do it one term at a time, but put it in parentheses so that the high is multiplied by the whole d low. So the derivative of x squared is 2x plus the derivative of 7 to the x. I know the derivative. Now, this is one that I don't actually have memorized, but I think I can figure this out. Because I know the derivative of e to the x is e to the x.
Yes.
So 7 to the x is going to be 7 to the x times something. It's probably the natural log of 7. Can I go off the screen?
Yeah, you can. I think it works.
Did it work? Okay.
Yeah. And this is, I think we were talking about this on via DMs. We were talking about how sometimes we don't know how to take, or we don't remember the rule for the derivatives, right? And I think it's important to, sometimes if you don't remember, just reference it. But I like that you went back and you knew the derivative of e to the x, and then you kind of, took a very good guess on how to take the derivative of 7 to the x.
Couple people in my comments, I don't know if they're commenting on your side, they caught my error with the squared. I didn't drop the exponent.
There you go. No, see, you were doing that to make sure they were paying attention.
Yeah, so good job. You all passed, both TB's TM and Math Nerd. You both caught it.
There you go. Nice.
Yeah, so up here, remember when I took the stuff squared, I brought the 2 out front to get 8. I need to drop the exponent by 1. And that's something about calculus is a lot of the times, especially with these more involved problems, the numbers, the pieces, there's a lot of parts moving around, and it's really easy to forget what you're doing along the way. And so taking a moment to go back and look, that's one reason I like to color code, so I can look really quick and I see my low is there. That's in blue. In brown is the derivative of the high. Now it's been fixed and I use the chain rule. In orange is my high, exactly like it looks. And then in pink is the derivative of the bottom. So now I can finish it off by just dividing the whole thing by the bottom squared. Now, do you want me to simplify, or are we going to call that good?
Let's not worry about it. But that's a lesson, right? That sometimes quotient rule comes with some caveats. You need to simplify the numerator stuff, and it gets super difficult and frustrating once in a while. But yeah, we'll leave it like that. I think hopefully everyone's good. My comments are saying it's good. So let's move on to the next one if you like.
All right. Okay. That was a good one. That was a big jump between the first problem and the second problem. I'm worried about the third now.
You know what? I was copy pasting the ones that I wanted to do. I didn't know this was number 2. So we might not even have time for all of them, but we'll see. Yeah. Okay. So see. Oh, you see, I accidentally copied this one. This is the same problem. The power rule. Yeah. So we won't do that one. Yeah. Let's try this one. I think.
Okay. That's a good one. So this one's a fun one to manipulate first and then take the derivative of, because I'm going to use logarithmic differentiation on this one. I don't know if that's what you intended, but one thing I notice, and this is where recognizing structure of problems is so important. When we're subtracting 2 perfect squares, that's a difference of squares, and we can factor that denominator to 1 minus the natural log of x times 1 plus the natural log of x. And the square root is the same as a 1/2 power on both of those.
Yes.
So
wow.
I'm going to look at this as y equals, or f of x equals, but I'll use y. X over 1 minus the natural log of x to the 1/2 times 1 plus the natural log of x to the 1/2. And the reason that's going to be helpful with logarithmic differentiation is we can take the natural log of both sides. And so I get the natural log of y is equal to the natural log of all of this stuff. But logs have some amazing properties that they can break up division, they can break up multiplication, and they can fix ugly looking exponents. And that's the whole idea here behind the logarithmic differentiation. If I were to use the chain rule on this, it would be a product rule with, it would be a chain rule inside of a product rule, inside of a quotient rule. And that's a lot of pieces. And I don't want to get lost again, like I did on the previous problem, where I just got lost.
Yeah.
So when I take the log the numerator logs are all positive and the denominator logs are all negative.
Yep.
But the exponents also move out front along the way. So I have 1/2 natural log of 1 minus natural log x minus 1/2 natural log of 1 plus natural log of x.
Awesome.
This is a lot easier derivative to take because the derivative of a natural log is just 1 over the stuff.
Yep.
And that's easy to do. So the derivative of natural log of y is 1 over y, but that's actually implicit differentiation. So I need to kind of chain rule it and use that dy dx in there. That's what we're trying to solve for. That's the derivative we're looking for in the final answer. And the natural log of x is 1 over x minus 1/2 natural log of 1 minus natural log of x. So the derivative of the stuff goes in the bottom. Mm-hmm. And then on top, I'm going to multiply by the derivative of everything that's inside there. Well, the derivative of 1 is 0. I like that one. The derivative of negative natural log is negative 1 over x.
It is.
So I'm going to move my 2, make some space here. Switching pens here. The negative and a negative will make a positive. And then the x is 1 over x. So that's going to move it down into the denominator.
I see.
So I did a couple things there all together. So the negative derivative is a negative is a negative times a negative is a positive. And the natural log of x, its derivative is 1 over x, and it's being multiplied by the derivative of the outside. So lots of pieces there.
A lot, yes.
And I'm going to do almost the same thing here. So maybe seeing it a second time will help. We've got the minus. The 1/2 puts the 2 in the denominator. The derivative of natural log is 1 over the stuff. So that stuff is 1 plus the natural log of x. And then I take the derivative of the stuff. This time it's going to be positive 1 over x.
Yeah.
And now I'm almost to my answer. I can't stop here because we actually have to solve for dy dx, which I'll do by multiplying both sides of the equation by y, giving me dy dx is equal to 1 over x plus 1 over 2x times 1 minus the natural log of x minus 1 over 2x times 1 plus the natural log of x times y. But we don't want y. Going back up to my green line up here, y is equal to the original function. So instead of y, I'm going to write what it's equal to, the original function. And since the original problem is even a more beautiful version of that, I'm going to do the x over the square root of 1 minus the natural log of x squared.
Awesome. I had someone comment that they felt that you had rewritten this step right here. I'm actually going to circle on my end.
Sure.
This part right here, the root 1 minus natural log of x squared. They were worried that you didn't bring the squared down. And that was just to reiterate that was difference of squares, correct? That you used?
Yeah.
Okay. Yeah.
Exactly.
That's what I had mentioned. That's awesome. This was a fun one. I was not going to do it as a natural log problem. I was just going to use quotient rule. That's what I would have done. But that just goes to show that everyone has different preferences. Yeah, I'm one of those psychopaths that like to use quotient rule.
And you can. And what's interesting is you get a very different looking answer.
Mm-hmm. You do.
Because to get our answers to be the same, I would have to distribute this ugly thing. Mm-hmm. And then I would have to get a common denominator and then combine all the like terms. And then our answers would look the same.
Exactly.
So that's a lot of ugly algebra to prove they're the same.
Yeah.
But, yep.
That's pretty cool. No, right away, I like that you use natural log. I think that is probably the best method. And I felt like if that was given to you on a test, that's maybe something that as a teacher you write, hint, use the natural log to make it easier on yourself or something like that.
Mm-hmm.
Yeah. Okay, cool. Let's go to the next one if you like. All right, let me erase my stuff too. All right. So let me know how you're doing on time. So that will be I can maybe move to some more difficult ones.
I think
Um,
we're good on time.
okay.
I'm got about 36 minutes left. I have a dentist appointment this afternoon that I get to run off to.
Oh,
I've got a hard stop in 36 minutes.
okay, perfect. That's great. Yeah, I'm the same way. So let's go ahead and solve this one.
All right. So again, looking structurally at what I see here, I see a whole bunch of ugly stuff is raised to a 6th power. So I'm thinking chain rule is going to be the best way to do this. We can bring the 6 out front and then times the stuff, no matter how ugly it is, raised to now the 5th power.
Yep.
And then the chain rule says we're what?
Don't get caught with that.
Not going to mess that up again.
Yeah.
Only once, so I'm going to make a mistake once. Then we're going to multiply by the derivative of what's left. And so I see this 7x, its derivative is just 7, plus, and with square roots in calculus, we actually don't use a lot of square roots. You almost right away are going to rewrite that as a 1/2 power so that we can use our exponent rules.
Right.
So I'm going to bring the 1/2 out front times x squared plus 3. It's a little more chain rule here, actually. Drop the exponent by 1. But then I have to multiply by the derivative of what's inside that square root.
Yes.
And inside that square root is an x squared. So its derivative is 2x plus 0 because the derivative of 3 is 0.
Nice. Nice.
And I will simplify the 1/2 and the 2. That's
there you go.
Reduction there.
Perfect. Yeah, this was a really clean one. I mean, it shows how to use the chain rule whenever we need to take the derivative. Wow, this is awesome. This is fun so far. I'm liking all your methods. I feel like you have a great way of explaining stuff.
Well, thank you.
Yeah. Okay. I mean, let's just kind of show this one. I feel like this was a pretty common problem that you'll see, especially when you're taking integrals.
Oh, man, the integral problem of this is just a classic. But right. The derivative one, I often see errors on this one a lot. This is the wrong way. I'm going to do this in red first. I see this all the time. People think that since the derivative of e to the x plus sine x, we take the derivative one term at a time, right?
Right.
So we should take the derivative one term at a time also. And this would be e to the x cosine x. And that is not accurate at all. It's a common error I see. And I think I see it a lot of the times with students who know the rule. We just get moving too fast. Right. That we fail to recognize the structure, that this is a product. And with a product, the product rule says this is actually going to come out as 2 separate terms. So we'll take the derivative of the first. I'll call this maybe g and h. We take the derivative of the first times the second like it is, plus the derivative of the second part times the first exactly like it is. So the derivative of e to the x is e to the x times the first sine x, plus the derivative of sine, which is our cosine, times the first, which is e to the x. And I'll just put it in front because it's prettier in front, but it would be fine in the back technically. Absolutely. I do see a lot of math books feel like they have to factor out the GCF, but I don't know why they do that.
Yeah, a common thing with a lot of my students too is they'll look at an answer or they'll get what you just got, and then they'll look at the book and they'll say, "Wait, I think I got it incorrect because the book wrote it differently." And that's just something that students have to, and especially in the AP Calculus exam, is being able to identify how you go from one of the answers and rewrite it so it looks just like the answer that's in the book. We can't forget factoring out the GCF. I think that's a common skill that we shouldn't forget whenever we're taking calculus.
Yep, 100% agree. And I think that's one of the most important skills in calculus is to be able to see how different looking things are actually the same thing. Because we do a lot of manipulating of the problem before we take the derivative or integral.
Right.
And sometimes we take the answer and do some manipulative just to make it look a little nicer and a little cleaner. And so just being aware of there are multiple ways to express the same right answer. It's very important.
I 100% agree with you. Okay, cool. Let's do, whoops. Okay, we did another. Oh, here we go. Here we go,
Woo!
Tyler. Here we go.
That's ugly. So I don't want to take this derivative the way it looks. It looks ugly. Fractions inside of fractions. That's way too much fractions.
Yep.
So I want to simplify this a little bit first. And one way we can simplify complex fractions is we can multiply the numerator and denominator by the same thing. Does not change the value. So I'm going to multiply numerator and denominator by x squared. So x squared over x squared is multiplying by 1. It doesn't change the value. And then it's going to distribute onto each term. So I like to write it 4 times just so that I don't forget to multiply by every term.
Like it.
And when I do that, it's going to reduce f of x. The squared with one of the x's leaves an x. X squared over x squared is going to leave a 1. X squared times x is x cubed minus x squared. And that's going to simplify everything down to a really nice quotient rule to simplify from here. So beautiful. Quotient rule, we've done one of these before already. We'll take the derivative of the top, which is just 1. That's really nice. Times the bottom. Minus the derivative of the bottom. And again, because there's multiple terms, I have to put it in parentheses. Otherwise, we don't get to multiply by the whole thing. I always tell students multiplication is very inclusive. So make sure everybody's included with multiplication. Addition and subtraction, those are exclusive.
Yep. Yeah.
So
whenever you're multiplying or dividing, they want to be part of the party. That's what I tell.
Part of the party. Students. I like that.
Yeah.
So we take the derivative of the bottom, 3x squared minus 2x times the top, x plus 1. And then we divide by the denominator squared.
Awesome.
And, I'd probably get rid of that multiply by 1 because that doesn't change things.
Exactly. Yep. And this is one of those instances, again, where because we're doing quotient rule, we might have to simplify the numerator.
Yep. And actually, I think an x would reduce out when you're done.
Yeah, it would. I think so, too. Mm-hmm.
So.
Yeah. When it comes to calculus, it's really interesting how people just forget about this negative value on the outside and forget to distribute it.
Oh, that's
parentheses. That's something that a lot of people just forget, and they might think obviously everything's not multiplied out, but that's huge when it comes to, or like that's a common mistake that I see with a lot of my students is they forget to distribute the negative sign.
Yep, and when I'm doing that in class, I'll often pull something from when we were adding and subtracting with negatives and say we're going to add the opposite. And so I'm just going to write in the opposite of both the terms in that next factor. And that way, when I distribute later, I'm not going to make a sign error because that's where they run into trouble.
Yeah, so you're not forgetting about it as we continue. That's awesome. Yeah, that's a great method too. Okay, cool. Let's go on to the next one. What kind of stylus are you using, by the way? It's really smooth.
Oh, I don't know. It came with the board. I have a Wacom tablet. My school
there you go. That's awesome. Yeah, no, it's really smooth. I like it. Okay, so we got the next one. It's almost like another quotient. Let's see. I know we got plenty of time, but I really want to throw one that can maybe we haven't seen.
Honestly, the 7 to the x is the one that had me the most nervous so far.
Really?
I was like, oh no, 7 to the x. Is it natural log of 7 or is it?
Okay.
I was glad I got that one. I was a little sweating on that one. Don't use that one very often.
All right. Yeah, this one's good, I think, with a radical.
Okay.
Yeah.
Excellent. So again, radical, I'm thinking chain rule because we know the square root of, I'll call it a. U, we like to use u for some reason. Square root of u or u to the 1/2 has a derivative of 1/2 u to the negative 1/2. So I'm going to use that to take all the stuff, 2x plus 5 over 7x minus 9, pull the 1/2 out front and drop the exponent. Then we have to multiply by the derivative of the inside. Well, the inside is just a quotient rule. And it's a really nice quotient rule because all the derivatives are constants. So the derivative of the top is 2 times 7x minus 9 minus the derivative of the bottom is 7 times 2x plus 5 on top, all over the bottom squared. Which means, if I might do a little bit of simplifying.
Yeah, I think we can do it.
So first thing I'm going to notice is the negative exponent is going to flip things over. Which means this is actually 7x minus 9 over 2x plus 5 to the 1/2. Right?
Yeah, perfect. I'm impressed.
Then I'm trying to get these 7x minus 9s to go together nicely. So I can put the 1/2 power individually on the numerator and denominator.
Okay.
Because they're factors, not terms. I can't put it inside the parentheses because those are terms. We had to talk about. Can't do that. But what's nice then is I can subtract exponents on the 7x minus 9.
Yes.
So that's going to give me 1/2 minus 2 is negative 3/2, which puts the 3/2 in the denominator. The negative moves it down. So then that's going to leave, there's still a 2 in the denominator. There's still a 2x plus 5 to the 1/2 in the denominator. And numerator is just this stuff left. So we've got 14x minus 18 minus 14x. Oh, look at that.
Yeah,
minus 35, right? So 14 minus 14 is 0. That's really cool. And 18 and 35 is 53. Testing my mental math here.
No, that works. Yes.
So yeah, it simplified kind of nicely.
Wow, that is, yep. Well, two things I wanted to talk about. So at what point, let's just say if you're great, you gave this to students, what will be an acceptable answer for you? Does it need to be simplified and look like you have it right now? Or would you, I guess my question is because I love how you canceled out that 7x minus 9. You put, you group those together. If a student had not seen that, would you be okay with it as a teacher?
So when I make my test, my philosophy on a test is every question is assessing a certain understanding. Can the student do this thing? And the next problem is, can the student do another thing? And so if I had a problem like this, I'd be looking for, can the student use the chain rule and the quotient rule together?
Got it.
If you got the blue line, you have shown me that you can do the chain rule and the quotient rule together. And so I would probably give full credit for the blue line, because on a test, my goal is just to say, can you do all the things we covered on the chapter?
Right.
Now, some instructors have different philosophies of test, and so they might want the full simplifying, but that's what I'm looking for in my classes. If any of my students are watching this live, I'm letting you in on a secret.
That's how you get your points. Exactly.
Yep.
There's actually this, I brought this one up because I had some students who had this teacher who made himself a lemma. He said he has his own rule for simplifying something like this. So the inside, like you mentioned, they're just binomials, and they have this form ax plus b over cx plus d, right? And when we take the derivative of this is what he created. He said the derivative is just a times d, so he ended up multiplying the a times d,
Mm-hmm.
minus c times b
Oh, yeah.
over cx plus d squared. He was so adamant that you had to use his lemma, is what he called it, which I thought was interesting. I'm like, okay, I guess it works, but you have to use a quotient rule to kind of go through the whole process of it. But
Mm-hmm.
that was his thing. He was so adamant that whenever he gave a problem like this, they had to use this shortcut. Yeah, but I thought it
Interesting.
was
And like I said, different teachers have different philosophies of tests and their purpose and how they're used. I can definitely see where this formula comes from because we ended up with the 14x and the 14x subtracting to 0. I don't know if you
right.
remember, I got excited that happened
Yep, I did.
because what my brain was processing is, I bet that happens every time. I
Mm-hmm,
bet that's a
mm-hmm,
pattern. And so my brain's processing, and that's the thing when you're starting to think mathematically, you're looking for these patterns to help you
mm-hmm.
solve more complex problems. And so then what I notice is we're doing 2 times 9. Well, gee, that's 2 times 9. And 35 was 7 times 5. We're doing 5 times 7.
Mm-hmm.
And so kind of noticing, and that's where my brain was processing, is this a pattern that happens all the time? Maybe I want to look at that more. And
Right.
that's where we want to try and get our students with all this algebraic manipulation. We force them to go through as we're
Mm-hmm.
trying to force you to mentally manipulate things and look for these patterns. Math is the study of finding patterns, identifying patterns, and using patterns to predict future events. And
Love it.
yeah,
Yep, that's a great way to describe it. Yep. I like to say mathematicians are lazy. We just want to create some shortcuts, once in a while.
yeah, exactly. It's all about the shortcuts because I'm not
Yeah.
doing this by the limit definition.
Oh no, 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 no. Yeah, I know. You have to
Maybe I should have done
torture
your
the.
first one by the limit definition. That would have been fun.
Yeah, we can do another one. That'd be really fun. But gosh, it's so interesting how when you first teach that to students, they got their response is always there's got to be a faster way of doing this, and I don't teach it to them until the very end until they
Right.
I'm confident that they know how to solve it using the definition of a derivative. Oh gosh, that's so funny that you well no one day we should attempt those. Um, okay, let's actually why not? This one is I feel like a lot of students getting correct, and I'm interested to see if that's the case on your end too.
Mm. So again, identifying structure first. That's really
Mm-hmm.
important on all these derivative problems. Cosine to the fourth is really some function to the fourth power. And so I'm going to take its derivative as if it's just something to the fourth power using that chain rule.
Yes.
So the 4 comes out front times my base, which is the cosine, and we drop the exponent by 1. So I've got 4 cosine cubed. And then we're going to multiply by the derivative of the inside, the derivative of the u, the derivative of the cosine, which is negative sine. So I'll move the negative out front.
Nice.
And then the other half is just a power rule. I lost the word for it. 4x.
There you go. Yeah. Um,
Excellent. I got some people solving these in my chat, and a couple people even beat me to that one. So excellent work,
that's
TB's TM.
nice. I think what we should do next time is I could even have this document online for people to download and they can work on it on their own,
Oh, there you go.
simultaneously. Yeah. Um, yeah, a lot of my students confuse the power of 4 and think it's a 4x. So cosine of 4x.
Oh, I could see that. Yep.
Yeah, for whatever reason, it's so interesting. I think trig notation is a very unique and something you have to get used to.
Yeah, and it's not clear.
Mm-hmm.
Um,
Right.
we've seen the sine inverse of x. Does that mean 1 over sine, which would be
Right.
cosecant?
Mm-hmm.
Or does that mean actually the arc sine, as I prefer to use, because it's more clear that I'm giving you the point, give me the angle.
Of course. Yes, absolutely. Um,
Terribly inconsistent. Yeah.
I completely agree. And then when people see cosecant CSC, they don't know how to say it, and they think it's the opposite of cosine. Just something
Oh
to get
yeah, the cos.
used
Yeah,
to.
yeah. I always tell students never pair 2 cos together. Opposites
Oh, that's a
attract.
great way of putting it. Yes, that is a good observation. Did I had one. I guess I didn't put it on the file. I'll find it in a second. But how much time do we got? We got plenty of time. Okay.
At
So I
16
got
minutes.
a yeah, implicit differentiation will be good.
Implicit differentiation is a great one because I think implicit differentiation hides product rules.
Mm-hmm.
And so students often miss where the product rule is actually happening. So,
Yeah.
for example, here, this x times y, I'll see a lot of students, this is wrong. Don't do this. They'll say the derivative of x is 1, and then it's dy dx is the derivative of y. And they miss the fact that that is a product rule. It's x times y.
Mm-hmm.
And that can look like a lot of things, x times y squared, x cubed times y to the fifth, whatever it is, but that's always a product. And so you have to use the product rule. If you're not using the product rule a lot with implicit differentiation, either you have a strange problem set, which is possible, or you might have missed it. So go back and watch for that.
Mm-hmm.
All right, so doing the product rule then, the derivative of x is 1 times the y, plus the derivative of y is the dy dx times the x. Oh, which kind of reminds me, I'm trying to remember, I've got a couple followers that have sent me some videos lately. One of them sent me a great video of doing the derivative of 1 over x, which was really funny. So
Okay.
before we wrap up, I have to show you this hilarious way to do the derivative of 1 over x, which is completely wrong, but it works, which is what makes it funny. You might have seen this.
Yes, it's a meme, correct?
Yes, it's a meme. Yes, and
I know
I
what
was
you're talking
cracking
about. Oh gosh, I know it works, but no, please don't do it that way.
but it works. Yeah, it's
Yeah.
funny because it works. It's like the old 64 divided by 4. No, 64 divided by 16. Cross out the sixes and it's 4, right?
Never knew that. Yep. Oh gosh.
But it works.
Yeah, exactly. Why not?
All right, I digress. Back to my implicit differentiation. All right, we did the product rule on xy. So we've done that term. Let's move over to y squared. We're going to chain rule y squared. It's 2y, but anytime we take a derivative with y, we have to multiply by the derivative of the inside, which is a dy dx.
Mm-hmm.
And then finally, we're going to end with the derivative of x cubed, which is 3x squared. Don't forget, we also have to take the derivative of the other side. It's a constant. The derivative of a constant is 0. Okay. Not done yet, though, because we need to know what dy dx is. We want to know how fast y is changing with respect to x. And so to do that, we're going to separate any term. Let me get a different color here. What color haven't I used yet? Purple. Every term with dy dx, we're going to keep on one side, and the others we're going to throw over to the other side. So throwing them over to the other side, we'll subtract a y and subtract a 3x squared.
Mm-hmm.
And all the things with the dy dx left, I'm going to factor out the dy dx and at least behind an x plus 2y. And then, I'm running out of colors. We can get the dy dx alone by dividing both sides by x plus 2y. And I get dy dx. My final derivative is, I'm going to factor out the negative because I think it's prettier, but you don't have to. But I like my answers to be pretty. Y minus 3x or plus 3x squared.
There you go.
I got out of both. Almost messed up there.
Yeah.
X plus 2y on the bottom. And that's how fast this function's changing at each point.
Oh God. Yeah, that's beautiful. I wouldn't know how this function looks like on a graph, but I'd be really interested in that.
We could throw it on Desmos.
Yeah, I have it here. I'll throw it as we do that, and then I'll bring it up. Okay, I guess we can do another one that I thought I had given you because I did not know the derivative for this one, and you're gonna see it in a second. Let me write it. Yeah, hold on. Let me graph this real quick for us. So xy plus y squared plus Desmos is amazing. I mean, I love using this thing. I'm surprised it's free.
It's so true.
Yeah.
And there's some amazing Desmos creators out there.
Oh, I know. You were just interviewing one, you know?
Yes.
Okay, I thought
Sir
yeah,
Bobert.
it's here on the screen. Yep. There we go. So,
Ooh.
I mean, Mathacol probably knows. Is this an elliptic curve? I really don't know. Most people would. I have no idea what this function is, but it's interesting. Kind of has like a nice,
I like the little
interesting
curve.
function to that. Yeah, exactly. Okay, so this was the derivative or the function that I thought was really interesting. Let me just go ahead. I'll just kind of erase this since I don't have it on me now, but it was y equals, and it was log base 5
Oh
of,
dear. That
you
one
know
ranks
what?
up there with 7 to the
Ex-
x. It's the same exact principle.
exactly. X squared plus 3, and let's just make it an over 5.
Hmm.
I
Let's
don't
see. I
remember
think
the derivative of logs.
so the derivative of natural log is 1 over x. So I wonder if it's 1 over the natural log of the base.
I'll look it up as I go.
Yeah, somebody maybe in the chat can confirm.
Yeah.
Because then if it was a base e, the natural log of e would go to 1, and it would simplify to 1 over
Yeah.
x. Yeah, so
Someone over
Bobert says yes.
yes, yeah, someone on mine was saying yes, so that seems
Okay.
correct.
All right, so we're going to go with that then. So again, looking at the outside, the structure is we've got a log base 5 of a bunch of stuff.
Mm-hmm.
So it's going to be 1 over, boy, this is going to get ugly. X, or 1 over the stuff, which is the square root of x squared plus 3 over 5, times the natural log of 5 as a constant.
Yep.
Then we have to multiply by the derivative of the inside. And inside is a square root, which would be u to the 1/2. So it'd be 1/2 times the thing to the negative 1/2. And I'm going to go ahead and say it's 1 over 2 square root of the stuff. Moving the negative exponent moving down, and then the 1/2 becoming a square root again, because that's actually going to help us simplify. Because I've got 1 over 2 times the square root of the stuff, which is x squared plus 3 over 5, which is going to be nice in a minute, because when we multiply these square roots together, there'll be no more square roots.
Yeah.
Which, now that I'm looking back, I wish I had seen this at the beginning, because it would have made life easier. If I had taken the square root and made it a 1/2 power, it could have come out in front of the log, and I wouldn't have had to worry about it at all.
Yeah.
No square roots in the front.
That's the beauty of math, though. You know,
Yep.
as you're working through the problem, you're like, oh, I could have done it differently, but you're still getting the right answer.
Mm-hmm. Exactly. So it'll all simplify the same either way.
Mm-hmm.
So the only thing left to simplify is this. Looking at the inside, that over 5 is a constant. So I'm going to pull out that 1/5 as a constant and multiply on top. The derivative of x squared is 2x.
That's it.
So a little bit of cleanup on there. We've got 2 in the numerator and 2 in the denominator. X is left in the numerator. Oh, this is interesting. This is a square root of 5, and that's a square root of 5,
Mm-hmm.
which multiply to 5, and then it's multiplied by 5, which equals 1. So all those 5s actually will reduce out.
Yeah, because it's one. Oh, yeah. Mm-hmm.
Which, now I go back to the beginning. I really could have made this a lot easier to solve. I'm going to take a second go at this one. We're going to redo this one the easy way after I'm done. Because if I had taken this as 1/5,
Mm-hmm.
we could have used log properties to make it minus the...
Yep. Yep.
Should have seen that. So this should have been a really easy problem, and I made it complicated because I didn't use my log properties. Hindsight. Okay. We're going to do it again the right way in just a minute.
All right.
All right. I'm going to move the natural log of 5 out front. And then the square root times the square root is just going to equal the stuff. And I think that's all the pieces, right? I didn't lose any pieces. That's a very easy thing to do in calculus, is to lose a piece.
Right. Yes. Keeping track of everything. That looks correct to me. I don't know if anyone in the chat is finding an error, but I think it looks fine. Yeah.
One person even suggested a change of base formula. I don't know if that would have made it easier.
That could have gone. Yeah, you actually could have done that too. Well, I think once you rewrite it and try to solve it the method you were thinking, you're gonna see that either change your base or this second method that you're about to show will make it a lot easier in general.
Yeah. So I would have started by rewriting this as log base 5 of, well, let's do it in a couple steps. We're going to do x squared plus 3 over 5 to the 1/2.
Mm-hmm.
And then exponent inside of a log can come out front. And then a log of a quotient is the difference of the pieces. So it'd be 1/2 times log base 5 of x squared plus 3 minus log base 5 of 5,
Mm-hmm.
which log base 5 of 5 is 1. And if I distribute through, we get 1/2 log base 5 of x squared plus 3 minus 1/2. And that's a lot prettier and a much easier derivative.
Exactly. Yep.
So, because the derivative of 1/2 is 0, so I don't even have to worry about that part.
Mm-hmm.
And then I've got the 1/2. The derivative of log is 1 over the stuff, x squared plus 3, times the natural log of the base we decided, right?
Yes.
And then I just have to multiply by the derivative of the inside, which is 2x. Reduce out the 2's, and that's the same thing we had
That is
before.
your answer. Yes.
Much easier, much cleaner.
I know, right? So fun. And to the person that had mentioned they could use a change your base formula, I believe that would have been this step. So you would have gotten the same thing if you did change your base formula.
Mm-hmm.
Yeah. Well, yeah, it would have been that one. Yeah, that
Yeah,
one.
change
This one's a
base
really fun
formula
one.
is really where we get the log formula from.
Correct. Yes.
Yeah.
Uh-huh. Awesome. Wow. Just with enough time to wrap it up. Gosh, this has been so fun. I mean, what's something that you would a word of advice for students as now that we solve these? What's something that you will tell them to look out for whenever they are taking derivatives now?
Sure. Well, what I would say, I've got this quote that I put on the top of all of my syllabi.
Mm-hmm.
It says, the difference between the master and the beginner is that the master has failed more times than the beginner has even tried.
Yes.
And I think it's really easy to see someone do derivatives and they fly through the problem and it looks so easy. The reason I can do these derivatives so easily and so quickly is I have done literally thousands of problems like this. And that experience from practice and just doing it, failing, learning from my failures, getting back up and dusting off my knees and going again, failing again and falling on my face, failing again and getting back up and learning from those failures allows me to move through these more smoothly. So really the big thing with derivatives is practice, practice, practice. Because the more you've taken, the more you start to recognize those patterns, the more you start to recognize what you need to do to be successful. You're not going to forget those little steps. You know, there'll always be little things that you make mistakes on because you're moving too fast. I had one on what was the second problem. I put a squared on when I shouldn't have squared.
Mm-hmm.
So don't worry about those little things, but focus on the progress that you're making. It's, learning calculus is a lot like running a marathon. The teacher runs the marathon and you're like, wow, you ran a marathon. What you don't see is that teacher has been in training for that marathon for months, if not years before that. And so practice, practice, practice. Don't be afraid of failure. Take risks, try things, learn, grow, and continue getting better. And you will be successful in the end.
There you have it. Yeah, persistence and just continue practicing. I love it.
Yep.
Yeah. Wallace or Tyler Wallace, thank you very much, dude. I think this has been so fun and informative.
Thank you. I had a lot of fun. Maybe we'll try
Yeah.
integrals next time.
Oh, okay. That should be a fun one. I'm interested.
As long as you promise that all the integrals can be solved with elementary functions. I don't want to do any air function Taylor series because that stuff gets a little crazy sometimes.
Okay. Anything up to separation by parts?
Yeah. That would include yeah. integration by parts,
Yeah.
partial fractions,
Oh, I like that. Okay.
all that stuff. That's fine. Nothing that doesn't, as long as it can be solved with an elementary function, we'll go with it. People always like to put things in my comments like, hey, can you solve this integral? And you can't solve it without an estimation Taylor series that's centered at 7 for some reason or whatever. And I'm like, yeah, I'm not going to make a TikTok about that. That's way too complex for a 30-second, 10-second TikTok. So
Exactly. Yep. Awesome. Well, I'm looking forward to that. I think that'd be really fun.
all right, excellent. Well, thank you very much. I've got to go
Anytime.
brush my teeth and go to the dentist office and hopefully
All
get a
right.
clean
Take
bill
it easy.
from him, cavity free, right?
All right. Yep. I agree. All right, Tyler.
All right.
Take it easy then.
Thank you. And thank you for
All
everyone
right.
for watching.
Of course. Bye.
Bye.
There you have it, guys. That was Tyler from Wallace STEM. Go ahead and give him a follow on TikTok. I believe he is also on Instagram. So hopefully we'll do a integral session sometime in the future. I think that'd be really fun. And if there's anything that you feel that we wanted to cover, or if there were any mistakes that you saw, let me know in the comments. And I will see you soon. Take it easy.